quel bellissimo posto.
Sì, in Messico.
In Messico, hai ragione.
Ma questi qua sono cristalli di quarzo o di calcite?
Infatti a Simone è interessato tantissimo, solo che non si può visitare, perché fa troppo caldo.
Sì, sì.
Ah, fa troppo caldo.
Sì, vedi, infatti loro hanno la tuta lì nella foto, perché...
Bisogna andare con delle tute speciali.
Ah, ti devi col...
Sì,
okay,
sì.
sì, fai...
Allora. Dunque. Prendiamo il link. Vediamo se uno clicca qui cosa vede.
Dovrebbe andare, sì. Sì, magari... Non va? Come mai? Provo a farlo un F5.
No, aspetta, proviamo a cercare. Dunque.
Però dovrebbe andare da quel link lì. Cioè se il link era ai live events. Oh, già
No,
si
no.
è mangiata la camera, eh?
No, non toccare niente. Aspetta, vediamo. Allora, facciamo accedi.
Sì.
Dunque, seminario nuovo.
Allora non c'è fisicamente lo speaker?
Allora, aspetta, rimettimi la password.
Sì, c'è.
C'è.
No, sì, arriva.
Una teleconferenza.
No. Dovrebbe arrivare... Buongiorno.
Ciao.
Non sprima niente.
Allora, ma adesso sei entrata come... No, scusa. Sono uscito, abbi pazienza.
Ma entriamo.
Sì, non so perché non... Sono uscito per sbaglio. Allora, il mio canale. Ok, dal vivo ora. Questo si vede, ma perché allora cliccando qui non si vede?
Perché cliccando lì? No, perché ti manda un altro link.
Porca miseria, ma perché?
Non so.
Allora devo rimandare l'annuncio. È cambiato?
No,
che strano.
assolutamente, no, assolutamente.
Watch, però è cambiato.
Sì, però non so come... Si sente?
Sì. Sì, si sente, quindi questo è buono. Niente, rimando il link.
No, infatti chiedevo, pensavo fosse una teleconferenza.
Allora.
Hai rimesso il link giusto?
No, lo devo copiare.
Adesso devo anche capire perché, in un altro momento.
Allora, era B. È cambiato.
È cambiato.
Ma allora cambia tutte le volte?
Ma non dovrebbe, però al limite creiamo, poi la prossima volta ci creiamo un evento come già facevamo, così sappiamo che il link è quello.
Scrivo così. E lo rimando.
Certo. Visto che funziona.
Deve essere tutto giusto, sì.
Ok.
Ok. Allora io spengo momentaneamente il microfono, così... lo
E
metti
poi,
in tasca in qualche modo.
sì, spero non sia troppo alto
Ti consiglio di non
nel...
metterlo fuori con la linguetta perché poi un po' di tempo fa è cascato. E
Ah,
ovviamente si è strappato il
proprio lo
giochino
metto
e
proprio in
quindi voglio
tasca
disegnare.
così allora.
Sì,
E on off è già on?
è già on,
Ah,
sì, sì.
perfetto.
Sì.
Quindi a questo punto non posso più dire niente che non sia... Ah, vedo l'ultima riga è un po' tagliata. Speriamo non abbia messo niente all'ultimo ultimo. Non dovrebbe esserci niente di fondamentale. Nel caso poi ve lo dico.
Credo che ci sia un eccesso solo per trarre un pochino più.
Intanto questa parte qui del video tanto la taglio, ovviamente non è che ci sono le
Sì,
robe.
sì,
Cioè,
mi
io poi
immagino.
lo taglio quando incominci a seminare. Ma certo, sì, c'era Alessandro lì.
Ah, Alessandro.
Cioè l'altro Alessandro.
Sì, sì. Giusto. Ecco qua.
Bene.
Ah, mettiamo il canale Alessandro.
Aspettiamo ancora? Forse sì, con delle viti. Con delle viti. Sì. Già ci vede lui il regista. Sì, sì, andrebbe un attimo. Andiamo? Sì, è perché... Ah, vi dà noia, con la luce lì.
Ah, non vedo così se dormono. Va bene.
Okay, good afternoon, everybody. We have the pleasure to visiting for a couple of days, the beginning of the week, Matteo Brogi, who is a graduate, master graduate from the University of Pisa in physics, in astrophysics, and has then moved to the Netherlands to gain a PhD with the Ignace Netherlands at the University of Leiden. And then he is presently, since about a year and a half or so, a Hubble Fellow at the University of Colorado Boulder. And today he's going to tell us a little bit about exoplanet atmospheres and the cunning way of getting information out of them. We'll have the talk in English as we have an English-speaking guest with us. Okay?
I was telling Alessandro it's actually better for me because I always talked about these things in English and I studied about these things in English. So it's actually the first time I had the pleasure to be on the Italian soil and be able to talk about high resolution spectroscopy applied to exoplanet atmospheres. Right, so let's give it a start. So a little bit of outline of what I want to talk about today. Yeah, I'll give a little bit of introduction at the beginning, telling you how you pass from finding exoplanets to characterize them, so to study their properties. And the key is for doing this is studying their atmospheres. And then I'm going to tell you how you can detect molecular species by using high spectral resolution. And as a byproduct of this, I'll tell you about how you can also measure masses and inclination of non-transiting planets in the process. And also, I'm going to explain how you can use high-resolution spectroscopy to constrain atmospheric properties, for instance, the presence of thermal inversion layers in the exoplanet atmospheres, planet rotation, and the presence of winds. And I'll close with some future application. I'm not going to touch all of these, but I'll show you some exciting things that we hope we can do with high-resolution spectroscopy in the future. Right. So I just want to start, of course, I think most of you know a little bit about this, but I really want to highlight that there are two techniques today that are dominant for finding exoplanets. The first one is radial velocities, and the other one is transits. So with radial velocity, what you do, you carefully look at the Doppler shift in the stellar spectrum caused by the orbit of the star around the center of mass. So the star is pulled by the presence of the planet, so it orbits around the center of mass of the system. So there's a periodic shift of the position of the stellar lines, and if you carefully study that, you can determine the orbital period of the planet, the semi-major axis A, and the orbital inclination. But since you don't know the inclination of the system, you have an uncertainty on the precise value of the mass, and only a lower limit for the mass can be constrained. Now, with the transit technique, this happens when geometrically you have the planet that is crossing the stellar disk. So if you carefully monitor the flux from the system, no, it's a problem. You have a small dip in the light curve, which is caused by the planet that is transiting in front of the disk of the parent star. And if you carefully study the shape and the depth of this transit curve, you can determine the contrast, so the contrast ratio between the area of the star and the one on the planet, and therefore infer the size of the planet. I will come back later on this in more detail. And I just want to highlight that this is not the state of the art of the measurements. This is the first radial velocity planet found around the main sequence star back in 1995. And this is the first transiting light curve. Actually, this is a nice story because this was taken, part of the data was taken from behind the astronomy department in Boulder. So there was a small telescope there, and one of the observations was done with a very small telescope. Right, so what I can do now that I have, nowadays we have over 2,000 confirmed exoplanets and many thousands of candidates that still await confirmation. If you put them on a semi-major axis, I'm sorry for this small part that is cropped out, in a semi-major axis mass diagram, you can clearly see that indeed transit and radial velocities dominate the discovery space, so in red and yellow. But what is important to notice is that this is a good plot, but I always tell everyone that it's a biased plot. And the reason is that there is a detection limit here, so the emptiness of this lower right corner is not real. It's not that there are no planets there, it's just because we cannot detect them yet. And also the other thing that is not real is the abundance of these giant planets orbiting very close to the parent star, which we call hot Jupiters. In terms of the number of known and confirmed exoplanets, this is a considerable fraction of the planets. But if you do the calculation, so if you account for the observational biases, and you derive the true exoplanet population, you can actually see that these giant planets are only a small percentage of the exoplanet population. Actually, the most common planets have intermediate radii between the radius of the Earth and the radius of Neptune. And this tells you that the most common planets basically have no analogs in the solar system. So this is quite a surprising result. And except maybe planet 9, we'll see about that in our solar system. And the other thing that is very important to realize is that now if you have radial velocities and transit measurements at the same time, Now you can constrain, you can solve for the orbital inclination, so you can get a true planet mass. You can solve for the planet radius, so you can start studying the density of the planet, the bulk density of the planet, and this is what happens here if I put the systems for which this measurement is possible in a mass radius diagram. And I also color-coded these points based on their error bars. So the darker points are the ones that have smaller error bars. So they are the ones that should guide you more in determining the trends. And you can see at least two also surprising things here, that the giant planets, so Jupiter mass, slightly more than 1 Jupiter radius, have inflated radii. So this is a pure hydrogen envelope. And as you can see, all these planets have radii that are bigger than what you expect from equation of state. And the reason is that there must be some form of depositional energy, extra energy in their interior, which causes the radii to inflate. The precise mechanism is not well known yet. It could be something primordial, so a delayed contraction of the planet. It could be that these planets are highly radiated, so in some way the incoming energy from the star gets deposited in the interior and causes this extra inflation. But it's important to realize that this is only visible when you start to access the density of the planet. The other thing that is important to see is that for small planets, so planets smaller than Jupiter, there's basically a huge degeneracy between the planet bulk in the planet bulk composition. The degeneracy works like this. So you can have a planet here with a denser core, so a denser core and a much more extended atmosphere, or a much lighter core, for instance, rich in volatiles like water vapor, and a much thinner atmosphere, and those planets would have the same density. So based on the density alone, it's very hard to tell the intrinsic properties, for instance, the internal composition and the atmospheric composition of the planet. So that's one of the first reasons why it's very important to access the atmospheres. Yes?
Short question about inflation, but this is also connected with the distance from planet to star. Right?
Yeah. So this is
This is true for hot Jupiters mainly, or only
the problem is that I don't think we have enough statistics on the, let's call it the warm Jupiters, because the observational bias, since these giant planets are not very common, the observational bias is to find the ones that are very close to the parent star because they're easiest to observe. So I don't know, maybe there is, but I'm not aware of a very clear trend with the stellar radiation. There is a little bit of I remember, if you plot, there is a cutoff value of the stellar radiation for which most of the objects tend to realign, below that value tend to realign with the but still a little bit inflated with respect to the expectations. Well, this is just for zooming in the Earth mass regime. So now you have planets from lower than 20 Earth masses and a few Earth radii. And this is a plot that I took from Berta et al. 2015. And you can see, you can maybe tell that there's a little bit of trend that the planets smaller than 5-6 Earth masses tend to align in an Earth or Venus-like composition, whereas there's a large spread once you go above this value. But this is not strictly true because you have a lot of objects that must be enriched in volatiles, even in this very simplistic picture. Right, so atmospheres. Well, the first thing that so we know the statistical properties of exoplanets, as I showed you before. We know that giant planets are not very common, smaller planets are very common, but we want to pass from statistical to individual properties of exoplanet. You want to be able to tell if you have a specific planet, what's the composition, what are the characteristics of that precise planet, and you have to access their atmospheres to do that. The other reason why it's important to access the atmosphere, as I just showed, is for solving the degeneracies between the planet interior and its envelope. And also you would like to start studying the composition of these atmospheres to link those to where the planet formed in the protoplanetary disk. So it's a complicated matter, this. It's not clear yet if we can do that, but there is hope that for these hot Jupiters we will be able to, once we measure the elemental abundances of carbon, nitrogen, and oxygen, to link that to where in the protoplanetary disk the planet formed. And eventually, of course, the field is progressing very rapidly. In a few decades, we might be able to say or to tell something about habitability. And of course, then the atmosphere is the fundamental parameter that you want to access, because the atmosphere is what eventually determines the surface conditions of an habitable planet. All right, so a little bit about how atmosphere are traditionally studied. Traditionally, studying exoplanet atmospheres passes necessarily through transiting planets, and the reason is twofold. So when the planet is transiting, the planet disk is blocking part of the stellar disk, but also you have the atmospheric ring. So what happens is a small fraction of the starlight filters through the planet atmosphere and gets imprinted of atoms or molecules that are present in the planet atmosphere. So what happens is that at specific frequencies, at specific wavelengths, where the atmosphere of the planet is more opaque, the planet will look slightly bigger, so it will block a slightly larger fraction of the stellar light. So if you measure the fraction of the stellar light that is blocked as a function of a wavelength, you can map the opacity in the planet atmosphere, which is called the transmission spectrum of an exoplanet. Then half an orbit later, what you have is that the planet is occulted by the star, and in this case, by comparing the light before and during and after secondary eclipse, you can infer the light that is coming directly from the planet, either in the form of thermal flux, so thermal emission from the planet, or reflected light from the parent star. And there's a third, it's not exactly a configuration, but it's a third measurement that you can do, which is following the total light from the system during one orbital period of the planet, and you can then build a phase curve which tells you the relative contribution between the night and the day side of the planet. And in principle, if you combine all these measurements, you can infer molecular species, their abundances, temperature pressure profile, and also the energy redistribution in the planet atmosphere. Now, I want to show a little bit of numbers, like the expected signal. So the depth of the transit is, of course, dependent on the ratio of the radii of the planet and the star squared. And for a Jupiter-Sun couple, it will be the depth will be something like 1%. It will be much, much smaller, of course, for the Earth. But what we are interested in, and in this case, is the change in this depth due to the presence of an atmosphere. And then eventually, an atmosphere is basically just a tiny ring. So this change is proportional to the area of this ring. So you have here, like, this change in transit depth is proportional to, again, to the ratio between the planet radius and the stellar radius. Then this is h, which is called the scale height, and basically is dependent on the planet temperature, on the planet gravity, and the mean molecular weight in the planet atmosphere. And then you have a number here, which tells you to how many scale heights, how many h, basically, how many scale heights you are sensitive to. And this is approximately dependent on the logarithm of the variations in opacity between one spectral channel and the adjacent channel. So imagine that you are in the continuum, which are probing very deep in the planet atmosphere, very low opacity, then you move to another spectral channel. So the number of scale height that you probe is proportional to the logarithm in the change of the opacity. And you will see this in a moment, because how do you maximize the signal then? Of course, you want bigger planets, you want warmer planets with lower densities, and you also want to find planets around smaller stars, because this is all going towards maximizing your transmission signal. And also you want to maximize the change in opacity between spectral channels. And the natural way of doing that is going to very high resolution. So passing from the continuum to a coronal line, like difference in opacity between the continuum and the coronal line is maximized in this way. So just to show you what I'm talking about, like, let's start from a low resolution spectrum. So this is a real transmission spectrum of an exoplanet. The exoplanet in question is HD 19733b. It's roughly a Jupiter mass, Jupiter size planet. And as you can see, these are real data. This is all space data. So data from Hubble Space Telescope. This is TISS. This is Wi-Fi Camera 3. And these are the IRAC bands on Spitzer. So there are some interesting features here, but what I want to show you is that you have a gray model for the planet atmosphere superimposed, and the wiggles in this model are really, really tiny compared to the error bars. Especially in this region, you might say that you could have every possible model pass. So the error bars are comparable to the variations in the transit depth. Now I'm going to show you the same thing, focusing on a very a narrow band around the K band, 2.3 micron, but a very high spectral resolution. So let's go to 100,000. Let's keep the same vertical scale, and let's see what happens to the spectrum. And what happens is this. Now you have 3 different species that are shifted for visualization purposes: carbon monoxide, water vapor, and methane. And what you can clearly see that the amplitude of this variation is huge compared to the low resolution spectrum. And the reason is indeed because we are now maximizing the change of opacity between the continuum and the core of the lines. But more importantly, in the previous spectrum, it was very hard to tell which is which, so which molecule would cause these small variations. But now at high spectral resolution, each specific molecule has a very specific fingerprint, so it's very easy at high spectral resolution to recognize the species which are responsible for the absorption by matching line by line. You will see in a moment that we use cross-correlation functions for that. So the first advantage that the molecules are resolved into individual lines, so you can definitely tell without uncertainty, without being ambiguous, which is the molecule that is causing the absorption in the planet atmosphere. The second advantage is shown here. You have wavelength still here. We are still around 2.3 micron. And this is a very simplistic toy model in which I showed a simulated observation from the ground. And what you have is that you have all these vertical lines as a function of time or orbital phase. And these lines are not moving with respect to the observer because they are formed in the Earth atmosphere. So their position in wavelength stays stationary, whereas the planet signal that I have shown here in white is changing in Doppler shift. And that's because the planet is rotating. While you observe, the planet is rotating around the orbit. So the other advantage that you have by using high-resolution spectroscopy is that you have a way of disentangling the telluric and planet signal, and this is because the planet is moving along the orbit. And this is an advantage because it's something that you can use to disentangle the contamination from the Earth atmosphere from the real signal that is formed in the planet atmosphere. And also, at the same time, you can measure the planet radial velocity for the first time. So we are not talking here about the stellar radial velocity, but the planet radial velocity directly. So instead of the hundred or tenths of meters per second of the star, we are talking about tenths or hundreds of kilometers per second, which is much easier to detect, especially at the spectral resolution. So if you're observing a transiting planet, you can do transmission spectroscopy, essentially the same way you do it at low resolution, and you can do the size spectroscopy just before or after secondary eclipse. But now in this case, you are really targeting the thermal emission from the planet directly, the thermal spectrum of the planet directly. So you can actually apply this method to non-transiting planets as well for the first time. And I'll show you in a moment what this means for the planet in terms of planet parameters. Right, so of course, like this is really, I cannot show you the whole data. I don't want to show you bother you with the whole data analysis. But as I told you before, there is a specific aspect which makes our analysis different from the others, is that we use the fact that the planet is moving along the orbit. So the Doppler shift in the planet spectrum is changing during one night of observation. And I'll show you here what happens. So this is real data. These are more or less 5 hours of data. Each row is a spectrum. So you have wavelength on the x-axis and you have time on the y-axis. And all these vertical lines that you see, these are telluric lines. So these are formed in the Earth atmosphere. We want to get rid of those. Now the key aspect, you can do that because these lines, as I told you, they stay stationary in wavelength. So we can process the data in such a way that we get rid of the telluric lines, and we are left, and maybe you can see these lented lines. This is a strong planetary signal that I injected on top of the data, and it is not touched by the analysis just because the planet is moving in radial velocity. So these lines are not absorbing always at the same wavelength, but the wavelength at which they absorb is changing in time. So once we do this and we get rid of the telluric, that's the second step that we do. We want to combine the signal of all the molecular lines into a single function. And the way we do that, we compute model spectra, and we cross-correlate the data with the model spectra for a range of radial velocities. And what we end up with is this panel here is this function. So this is the strength of the cross-correlation function as a function of, sorry, is now here, radial velocity and time. So essentially, this is a portion of the radial velocity curve of the planet. Now, the third step and last step is to get the total cross-correlation signal, which implies summing these cross-correlation functions in time. There is just one problem that if you know the orbital velocity of the planet, this is easy. You know at each instant which is the radial velocity, you shift the cross-correlation functions to the rest frame and you sum in time. For a non-transiting planet, you don't know the radial velocity, so you have to assume all possible radial velocities for the planet. That in this case means all possible slopes for this curve. For each one of them, you shift the rest frame and you coed, and this gives you this kind of final matrix. So you have the total strength of the cross-correlation signal as a function of systemic velocity or rest frame velocity and planet radial velocity. Now, this is the case of tau bodies B. I'm going to explain a little bit more about this. This is a non-transiting planet which we observed as a first test case for this method for 3 nights, and we observed just before, during superior conjunction, and just after superior conjunction. And what you see here is a signal that is maximized from carbon monoxide, which is maximized at the known systemic velocity of the system, which is minus 16 kilometers per second. And there is the measured planet orbital velocity is 110 kilometers per second. So now you have the stellar radial velocity, which it was previously known, and you have the planet radial velocity. What you can do like in spectroscopic binaries. You can put the two together, you get the mass ratio between the planet and the star, and if you have a good estimate for the stellar mass, you also get a good estimate for the planet mass. And of course, in this way, you can also solve for the orbital inclination. So for a non-transiting planet, which before was not observable, you can detect molecular species in the atmosphere, and you can determine true planet mass and orbital inclination for the first time. And this is not an isolated case. In the past, well, it's like in 5-6 years, we have detected, it's a small sample, it's only 6 planets, but you have to realize that it's a very small group of people working on this. It's like 4 or 5 people full-time working on this. I think so it's remarkable that in just a few years we could detect carbon monoxide, water vapor in basically 9 of the 10 data sets that we analyzed. And there are a few surprises as well. For instance, we never detected methane and carbon dioxide yet. Carbon dioxide is maybe not surprising because I think the equilibrium abundance is too low to be detected. But there is hope, at least for some of these planets, we should have seen methane. So it's still we'll still have a little bit of doubts if this is something astrophysical, or maybe the line lists that we use for generating the models at high spectral resolution are not so accurate once you go to the high temperatures, which are representative of these hot Jupiter planets. This is something we are still working on. So this is for what concerns the molecular species. Now, what can you say about the planet atmosphere? So there's our models are in some way they're comparable to other groups, but for someone that is used to work in the solar system, those are extremely simplistic. So we start, we basically parameterize the planet atmosphere in, so there are 2 isothermal layers, and then in between, the temperature can either decrease or increase with altitude, or it can first decrease and then increase. And there are only 3 points that you can vary in temperature and pressure. And for each one of these points, you can assume molecular volume mixing ratios for 4 species that we consider in this study. And then you solve the full radiative transfer and they produce the output model. Then you use for cross-correlating the data. So what we actually measure, we measure 2 things. First one is through the cross-correlation technique. You basically measure the degree of match between your data and your atmospheric model. And then, this is a little bit more complicated to understand, but you have seen before that I have renormalized essentially my data to get rid of the telluric lines. So we lose all the information on the absolute fluxes. So we don't know where is the planet continuum, we don't know where is the stellar continuum. What we still know is the depth, the relative depth between a core of the planet lines and the continuum. That is preserved from our analysis. So we can measure these 2 things, and let me skip this for a moment. So what this means is that, let me skip this as well. So high-resolution spectroscopy is is a tool that you can use for distinguish where an inversion layer is present in the atmosphere on an exoplanet. And the reason is that basically, very simply, you have the continuum that is formed at high pressures and a certain temperature, and then you have the core of the lines that is formed at lower pressure, basically giving you absorption lines in the case of a non-inverted temperature pressure profile. But when the temperature actually increases with altitude, you have the core of the line which is formed at a higher temperature, and that gives you emission lines. So there is no ambiguity at high resolution in distinguishing when you have an emission spectrum or an absorption spectrum. Actually, at zero order, if you try to cross-correlate the data with an absorption spectrum with an emission spectrum, you get anti-correlation. So it's very easy to distinguish if you are actually seeing in the data emission lines or absorption lines. And the result is that we haven't detected any emission lines in this planet. So all these planets observed have shown absorption lines, which is surprising given theoretical predictions, but is not it's kind of in line with other observations at low spectral resolution. So up to now, at the moment, there is no clear evidence of the presence of strong inversion layers of any of the exoplanet atmospheres that we have observed up to now. Let me go. This is one of the last things that we did with high resolution spectroscopy, which is measuring planet rotation and winds. And this is very interesting because this hot Jupiter, so these giant planets very close to the parent star, are supposed to become tidally locked on a very short time scale due to tidal interactions with the parent star. And so what this means that the orbital and the rotational periods of these planets should be equal. But on top of that, theoretical models predict two main regimes of atmospheric circulation. At lower pressures, you have, at lower altitudes, you have equatorial superrotation. So you have the planet rotating and an equatorial band that is super rotating with respect to the bulk of the planet. And at higher altitude, you have a global day to night side winds. So the wind is flowing from the day side to the night side through the planet terminator. So actually, at high spectral resolution, these regimes of atmospheric circulation and rotation should have an effect on the line profile of a detectable effect on the line profile of the planet, and that would basically broaden or distort or shift the planet line profiles. So what I wanted to do is to see if actually with real data I could detect these effects and measure planet rotation and winds in an exoplanet atmosphere. And I took again this planet that I showed you before, HD 19733b, and what happened is that it was relatively easy to detect two molecular species with the method that I showed you before, so water vapor and carbon monoxide, and that combined absorption as well. This for exoplanet community is kind of a reliable level of significance, so we are above 7 sigma, so it's something quite strong. But we wanted to go farther, so we wanted to study the rotation and winds. I needed to model the planet line profile. So I would like to show you a movie, but I think this is okay. Now, you can see this is a very simplistic model that I did. I assumed rigid rotation. I added an equatorial superrotation to this planet. And I did not model day to night side winds because since these winds are flowing towards you, the net effect is a blue shift of the cross-correlation function, which you can detect directly on the data. You don't need to model that. Now, you can see here what happens. This is kilometer per second. You can see what happens to the planet line profile when you have no rotation. This is during the planet ingress. So the planet is going this way, and here is just entering the planet disk. So in the case of no rotation, you have a perfectly symmetric profile. In the case of synchronous rotation, you have a broadened profile, and it's slightly red-shifted. And this is because this side of the planet is rotating away from the observer. Then if you assume an even faster rotation of one day, you can see that this red shift is even more pronounced. And then you have synchronous rotation plus jet stream. You have a side lobe for the planet line profile. Now let's go forward. When the planet is at the center of the disk, you still have the same narrow profile in the case of no rotation, and then you can see the profile is broadened and now symmetric because the planet is exactly at the center. And you can still see the side lobes caused by equatorial jets. And then when he exits, now you have a net blue shift of the planet line profile. So there is an extra radial velocity component and an extra distortion in the line shape that you might hope to detect in this data. There's only one problem, that the analysis was more complicated than this, because we actually work in cross-correlation space, and the cross-correlation is like is a broadening operator. So you are not actually measuring directly the line profile, but you are measuring a convolution of the line profile with the natural profile, our models, and so on. So we had to find, I'm not entering into the detail, but we needed to find a way of comparing the cross-correlation functions of models to the observed cross-correlation function. And we finally managed that, and then we could basically study how well our models were matching the data in a goodness of fit way. And the result of this is a full chi-square maps of fitted parameters. And what you have here, unfortunately, Scott, I also have to look. So you have the planet radial velocity. So this is the orbital motion of the planet. Then you have the planet rotational velocity, so how fast the planet is rotating. And here you have the same planet rotational velocity, and you have the equatorial excess velocity, so the jet streams, equatorial jet streams in the planet atmosphere. And the star is our best fitting value, and the diamond is what you will get for synchronous rotation from the literature value. So one thing is evident is that within 1 sigma, this is the 1 sigma contour, our data is indeed consistent with synchronous rotation. So the data favors models that are consistent with the fact that the planet is synchronously, tidally locked to the star. But there is an uncertainty, because we are very good in constraining fast velocities. So for instance, rotational periods less than 1 day are excluded at the 3 sigma level. But since the instrument has a finite resolution, we cannot very confident at this level of signal to noise. It's not easy to exclude slower rotation, so lower rotational velocities, and eventually even no rotation is only marginally excluded. So this is a physical limitation given by the resolution of the instrument, and given the low signal to noise of our data. If you would accumulate more transit and more data, you would be able to constrain this better. The other thing that you can see is that we are not good at all in constraining equatorial superrotation for this planet. So essentially the whole parameter space is consistent within 1 sigma. The last thing that we could measure, although it's a very small blue shift of the cross-correlation function, so there seems to be a little bit of a day-to-night side wind flowing towards us. And this is totally inconsistent with one of the optical, of the measurement of the winds that was coming from optical high-resolution transmission spectra, and it's consistent with another measurement. So the difference between these two is that in the case of Wittenbach, the authors did not remove the contributions from spurious stellar noise. Unfortunately, I cannot go into the details, but in our case, and in the case of Loudon et al., we removed the contribution of this spurious stellar noise, and we got the same value. Now, the question remains whether spurious stellar noise is capable to produce a spurious blue shift. But what I wanted to stress is that if this were true, basically, since optical high-resolution spectra probe much higher in the planet atmosphere, what you could get, you could pair near-infrared observations and optical observation actually study not only the day-to-night side wind, but also its change with pressure, with altitude in the planet atmosphere. So you can start to see the wind shear, the strength of the wind shear in the planet atmosphere by observing at different wavelengths, so from the optical to the near-infrared. And let's glide on this for a moment. All right, this is for the present. I want to show you something for the future. I want to show you how you can actually combine high-resolution spectroscopy with high contrast imaging, so direct imaging. So this is a very beautiful image of Beta Pictoris b. This is a very young planet, it has been imaged. So we knew from the 90s that there was a protoplanetary disk around the star, and then in the early 2000s, the planet was finally imaged. And then the planet moved, and it went too close to the star to be imaged. And then in November 2009, it went out again. And now we have basically one full half orbit for this planet. So these are direct imaging. So this is almost at the time state-of-the-art direct imaging techniques. What we wanted to see if we could combine high-resolution spectroscopy with direct imaging, and what we did, we went at the VLT with Critters, and so this is what you will get with the state-of-the-art direct imaging. So the star is completely cancelled here, and you have the planet detected at some distance below it. If you will go to the VLT, which doesn't have a state-of-the-art adaptive optics system at the same telescope where Critters is mounted, you will get something like this. So completely confused. There will be no possibility of separating the light of the planet from the light of the star. But now what we did, we added the slit. We took the spectra. Now these are real spectra. This is not real, but these are real spectra. And then we, from each position, each spatial position along the slit, we subtracted an average spectrum, and you basically end up only with noise. But now you cross-correlate at each of the positions. You cross-correlate the noise with a model for your planet atmosphere, and what you get is nothing everywhere, including in the star position. But at the planet position, you get a strong cross-correlation signal, which is indeed caused by CO absorption in the planet atmosphere. And this is not finished because you know which should be the narrow profile given the instrument, and we measure a much broader profile. So this was interpreted as rotational broadening by 27 kilometers per second, which means this planet must rotate in only 8 hours of a rotational period, which is indeed consistent. This is a young planet, so it's still contracting, still rotating much fast. It's rotating fast, sorry. And this is actually a test for the next decade, because if you can combine the contrast that you reach from high contrast imaging and the contrast that you reach in the spectral domain by high resolution spectroscopy, we hope that with the next generation of instrumentation, you could get to 10 to the minus 9 planet to star contrast, and this will give you the possibility to access terrestrial planets in the habitable zones. And we did a simulation for this. This is data from simulated data from a future ELT with a MATIS-like instrument. And this is the plane of the sky. This is a planet a little bit, is not exactly the Earth. Not by chance we took it a little bit bigger and a little bit warmer than the Earth to make the signal stronger. Orbiting Alpha Centauri B. And as you can see, this is traditional imaging. There's a lot of noise, speckle noise around the star. There is something maybe here, but there's not a high significance detection. Now you do the game that I explained you before. For each one of these pixels, this is an integral field unit, so you have a spectrum. You cross-correlate the data, and now in cross-correlation space, when you slice the cross-correlation space exactly the radial velocity of the planet, you get 8 sigma detection in, this is not only 30 hours of telescope time, but you have to realize that this is a terrestrial planet observed with ELT. So it's something that you could probably do by combining traditional imaging and integral field spectroscopy and a high-resolution spectroscopy, something that MATIS can do. You could potentially do something like that in the near future. Something else I want to use to close this presentation is, I told you before that for maximizing the transmission signal, you need bigger planets, but you can also go around smaller stars. And actually, this is very convenient because M dwarfs, which are much smaller than our sun, are the most common stars in the solar neighborhood. So there's actually a good point in searching planets around M dwarf star. This is not the only good point, but in terms of signal, there's a huge gain in doing that. Then what happens now? Let's put the Earth around an M dwarf, an M5 dwarf, and let's look for oxygen at 760 nanometers. And this is on the same scale. So this is carbon monoxide that we already detected in tau bodies B, is the detection that I showed before. This is oxygen. So there's only a factor of 3 of difference. So you might say a high spectral resolution. So you might say, well, let's go to more. Let's observe this. The problem is that tau bodies is K magnitude 3.4, and statistically, maybe the closest M dwarf hosting one of such planets will be 10 or 11 magnitude. So it means that you have a gap in magnitude to cover, and this means that you really need an extremely large telescope plus high resolution spectroscopy if you want to attempt this. And you cannot read this, but you need the ELT and 30 transits, which means 3 years of observations to get only a 5 sigma detection of this. So it's challenging. It's a lot of telescope time. but it shows that it is feasible, and then I leave to the astrobiologists to tell me if oxygen alone is a good it's a good biomarker. Probably it is not, but the message is that you can start doing something like this with ELT, high spectral resolution. And this basically leads me to the conclusions that I haven't touched all of these. I just want to show you that high-resolution spectroscopy can truly do a lot of things. There are two things that I haven't touched, which is the relative molecular. You can measure relative molecular abundances too in the planet atmosphere and derive the elemental abundances of carbon and oxygen for these hot Jupiters. And this is really important to connect the evolved state of planets, so where the planet is now, to where the planet formed in the protoplanetary disk. And also something that I haven't said is like this technique is really ideal to complement JWST in the future for the brightest targets that will be found by JWST, because it will be very hard to follow up these targets from the ground with traditional techniques. But these techniques, does not need reference stars. The data analysis, the observational strategy is really easy. And so I think it's really the best candidate for following up and complementing space telescopes in the near future. And this is actually what we are doing here, because we are trying to use the current next generation of instruments, for instance, JAN or the TNG, and see how you can extend all these beautiful techniques that I show you, how you can extend it to a new generation of instrument. And so this is all preparation for the coming years, and we hope to achieve very interesting results. And well, this is all, and I'll take questions from here. Thanks.
Any questions?
Yeah. Excuse me, I'm not working in this field because I'm a solar physicist, but I don't understand when you have the planet occulting the sun, what you showed is a very flat sun, like the sun if you observe it at 5,000 angstroms.
Yeah.
But if you go in the infrared, like 10,000 angstrom or even more, the sun is highly structured because you have filaments, active regions, and everything. So I don't understand how you can disentangle the effects related to the fact that the planet is occulting different features on the star with variations due to the planetary atmosphere.
So if you would do a traditional light curve, so out of transit, in transit, you would not be able to do that. And that's actually the accounting for the stellar noise is something that currently many people are working on. And also all these substructures that you were mentioning will have an imprint in the light curve, because you are measuring the depth instantaneously compared to a depth out of transit, so the total light of the system. So of course you will be influenced by this, and you will be influenced in the long term also on by the stellar variability that you have. In this case, the situation is less serious, because what you do at each instant, so at each interval, you basically renormalize your data. So you take the continuum level that you have in your data, and you use it for the normalization. So at each instant, you are truly referring the depth of the core of a planetary line with respect to the local continuum, which is a combination of the planet continuum and the stellar continuum. So if something changes in the stellar flux, this will be automatically, in such a small spectral range, it will be automatically accounted for by the renormalization process.
Even spectroscopically, even in the sun, if you move with narrow band spectroscopy in absorption lines, you are sampling different layers of the atmosphere of the sun.
Yes, but we will.
How you disentangle?
But in Doppler space, well, this is probably not technically completely true, but we are comparing the tens or hundreds of kilometers per second of shift in the planet signal to the stationary telluric and quasi-stationary in this regime stellar absorption. So everything does not move in wavelength is automatically removed by the data analysis. There is one caveat to this. So of course, every star is rotating, and in the stellar spectrum, there will be spectral lines. For instance, in the case of carbon monoxide, there will be the same spectral lines that we are looking for in the planet spectrum. In that case, there is actually a non-stationary stationary component, which is given by the Rossler-McLaughlin effect. So the star is rotating, the planet is crossing a chord along the stellar surface, so it's occulting a rotating stellar surface, which means that if you look at the stellar line, that will be distorted a little bit, and the distortion will change during the transit because the planet is occulting a specific portion of the planet atmosphere. So this is something that we have to account, we have to model if we want to look for these molecules like carbon monoxide, and we have to remove from the data. If we do not do that, that's a serious source of spurious noise, and this is the reason why I show you the two detections of sodium, and one gives a -8 km/s and one gives -1.5. That's because in one case the group removed the Rossler-McLaughlin, so this stellar spurious stellar noise, and in the other case that was not accounted for. So indeed, the stellar variability can be as not even variability. The stellar spectrum can be a source of noise.
So, thanks first for this great talk. So my question is, what's the range of altitudes that you are probing with the very narrow range of priorities? In the sense you said you didn't find any temperature inversion or superrotation in H2O, but this maybe is only due to the fact that you are probing a small range of layers in the atmospheres.
Yeah, so in typically thermospectra, which have the biggest dynamic range in terms of pressures, the continuum sets between 1 bar and 0.1 bar, and in the K band. And the core of the lines, it depends on the molecular species because it depends on the opacity, of course. But the CO lines, which have the highest opacity, go up to 10 to the -4 or 10 to the -5 bars in the planet atmosphere. So it's still possible to have an inversion, like a high altitude inversion. But what you can't have is the type of inversion which involves like a considerable fraction of the atmosphere, which is predicted by some of the theoretical models. An inversion of 3 or 4 order of magnitudes in pressure, that's definitely not possible because we would have seen that we have tried to inject artificial data. We would have seen that in the data at the 8 or 9 sigma level in the data sets that we have analyzed. So local, a high altitude inversion is still possible, but not something that involves a large fraction of the planet atmosphere. If that answers the question.
As for the rotational velocity of the planets, you assume that the rotational axis is parallel to the perpendicular to the orbit.
Yeah.
Otherwise, you only get an upper limit to the.
Yeah, this is due to the fact that for tidal effects we expect in these evolved systems to, if you move away from the star, and you basically if there is no full synchronization, then of course, yeah, you have an uncertainty on that. Also, this is a very, I should say that this is a very simplistic model because it assumes complete symmetry in the velocity field along the planet terminator, whereas realistic models predict that actually the red and blue shifted, let's say, velocity field along the stellar terminator is really asymmetric. So what I'm trying now is to implement more realistic models coming actually from the physics, rather than parameterizing them as I did in this first case.
So it would probably be interesting to be able to measure very highly misaligned systems.
Yes. Yeah, this is something. The real problem is that for this type of measurements, you really need a high spectral resolution. And currently, well, CRIRIS is off the telescope, so we have a lack of really high resolution, except for the optical. In the near infrared, we have a lack of high resolution spectrographs going to 100,000 like this. So for detections, like JANO, for instance, will be great for detections, but being 50,000, you will lose the precision in this type of measurements.
None, then let's thank Matteo again.
Thank you.